The Thevenin and Norton equivalent for AC circuits is similar to the Thevenin and Norton equivalent for DC circuits. So the process is as follows. First, are there any dependent sources? If so, turn off the independent sources, add a test voltage source or test current source across terminals A and B, and then use the mesh current or node voltage method in order to find either the voltage across or current through the test source, and then use that to find the Thevenin resistance or the Thevenin impedance, Z Thevenin equal V test over I test. Then the next question are there voltage sources in series resistors or current sources in parallel with resistors? If so, then you can do the source transformation method and attempt to simplify the circuit down to just a voltage source in series with an impedance or a current source in parallel with an impedance, which would be the Thevenin or Norton equivalent. If you don't have that, then what you would do is turn off the independent sources if there are no dependent sources to find Z Thevenin, or leave all the sources on and use the mesh current or node voltage method to find the open circuit voltage across terminals A and B, which is V Thevenin, or the short circuit current through terminals A and B, which is I Norton. And then you can use those two to find Z Thevenin, which is V Thevenin over I Norton. And then you can draw the Thevenin equivalent circuit or the Norton equivalent circuit. Remember to also consider dummy resistors or any resistors that are dangling resistors when you do the source transformation method. Okay, let's take a look at what this looks like for AC circuit analysis. Lecture 4.2, AC circuit analysis, source transformations, Thevenin and Norton equivalents. You should be reading section 9.7 of your textbook. Upon completion of this lecture, students should be able to use source transformations to solve for unknown voltages and currents in a circuit, and also to find the Thevenin and Norton equivalent of a circuit. Recall that source transformations are based upon the equation V equals I times Z, and that we state that two circuits are equivalent if you put an ohm meter, voltmeter, or ammeter across two nodes across the circuit and they read the same values. It is possible to use source transformations to simplify or reduce a circuit to solve for unknown voltages and currents, as long as you have a voltage source in series with an impedance or a current source in parallel with an impedance. It is also possible to find the Thevenin or Norton equivalent for a circuit in the frequency domain that contains both independent and dependent sources by using the following figures or reviewing the configuration for Thevenin equivalent and Norton equivalent circuits. You can also use source transformations to find the Thevenin and Norton equivalent when you don't have dependent sources. So the following two figures show the Thevenin equivalent and Norton equivalent for a circuit. Notice that the Thevenin equivalent is a voltage source in series with an impedance, and the Norton equivalent is a current source in parallel with an impedance, and you can transform between the two of these by using source transformations. Example 1, using source transformations, find the Thevenin and Norton equivalent for the following circuit, and we're going to start by converting the 40 volt source in series with 1 plus J3 into a current source in parallel with 1 plus J3. And in order to find the value of the current source, you use 40 divided by 1 plus J3. So the value of the current source is 12.65 with an angle of negative 72 degrees. So after calculating the current source, we draw the circuit with the current in parallel with 1 plus J3, in parallel with 9 minus J3, in series with 0.2 plus J0.6, and then all of that in parallel with 10 minus J19. So next we're going to combine 1 plus J3 and 9 minus J3 in parallel to get the impedance 1.8 plus J2.4 ohms, still in series with 0.2 plus J0.6, and all of that in parallel with 10 minus J19 ohms. So next we're going to do another source transformation to convert back to a voltage source in series with an impedance. So the impedance is going to be 1.8 plus 0.2, which is 2 ohms, plus J 2.4 plus J 0.6, which is J 3 ohms. And then we're going to have the 10 ohms and the negative J 19 ohms again. The value of the voltage source is found by using 12.65 with an angle of negative 72 degrees times 1.8 plus J 2.4, which yields the value of the voltage source as 3.79 with an angle of negative 18 degrees. Now we're going to do another source transformation to change back to a current source in parallel with two impedances. So the first impedance will be 2 plus J 3 ohms, and the second one will be 10 minus J 19 ohms, and the value of the current source is 3.79 with an angle of negative 18 degrees divided by 2 plus J 3. So the value of the current source is 1.05 with an angle of negative 75 degrees. Our next step will be to combine the impedances, so the current value is still the same, and the impedance is going to be found with 2 plus J 3 in parallel with 10 minus J 19, which yields 2.63 plus J 2.84 ohms. And that is also the Norton equivalent circuit. Then we do a final source transformation to get the Thevenin equivalent circuit, and the Z Thevenin is 2.63 plus J 2.84 ohms, and the value of V Thevenin, the Thevenin voltage, is 1.805 with an angle of negative 75 degrees times 2.63 plus J 2.84, which is 4.06 with an angle of negative 27.8 degrees.